Welcome to QuadLab Mesh Cleaner version 1.0.0. Part 1. Analyze Mesh. Let's open the object we want to clean up. First, we'll apply all transforms. As you can see, we're working with a fairly complex and messy mesh. Next, let's enable face orientation so we can clearly see which side of the surface is facing outward and which side is inverted. Now we'll open the already installed QuadLab Mesh Cleaner add-on and also enable the Mesh Diagnostics overlay display. The panel appears, but to display the data, we first need to run the diagnostics. So let's click Analyze Mesh. In our case, the analysis took about 3 seconds. We've now received a detailed analysis of the mesh. Mesh Cleaner can detect problematic elements such as loose vertices, loose edges, loose faces, tiny fragments, small islands, boundary edges, boundary loops, open borders, tiny holes, large holes, non-manifold elements, inconsistent normals, self-intersections, n-gons, degenerate faces, and near-zero edges. We also get detailed general information about the mesh. Let's note the current vertex count before cleanup. 70,329 vertices. There is also a separate Mesh Diagnostics tab in the end panel where you can inspect each problematic element individually. If an issue is found, you can zoom in on it using the Inspect button. This will focus on the first randomly selected problematic element. This feature can be very useful when the algorithm cannot automatically resolve certain artifacts, and some manual repair is required. You can also find important additional information in the Mesh info block. Pay special attention to the zero values for edge length min and face area min. Once the object has been analyzed, we can move on to the basic cleanup stage. Part 2. Basic Cleanup. Basic Cleanup repairs most of the problematic parts of the mesh. Here we gain access to several settings. Small Island Threshold removes detached islands with 10 or more faces when their total area is smaller than a specified percentage of the main island's area. It does not affect isolated single-face islands or tiny fragments made up of 2 to 9 faces. Merge distance can be enabled or disabled, and it allows you to define the maximum distance between vertices that will be merged together. In our case, we will set merge distance to 0.0025. This value was chosen deliberately because in the Mesh Info panel, we can see that the edge length is 0.0028. In other words, this lets us eliminate edges that are shorter than roughly the average value, while still leaving a small margin so that the vertex merge is not too aggressive, but remains close to the average edge length. There is also an option to triangulate n-gons, where you can define the edge count limit for n-gons that will be triangulated. If this option is enabled, you can also choose the triangulation method. Now let's run Basic Cleanup. The basic mesh cleanup takes quite a long time. Improving this is one of the priority tasks planned for future versions of QuadLab Mesh Cleaner. As a result, we can see that all loose faces, tiny fragments, some boundary loops, almost all tiny holes, all degenerate faces, and all near-zero edges have been removed. However, new boundary edges, large holes, non-manifolds, self-intersections, and n-gons have appeared. This is normal because repairing one type of artifact can sometimes create another. In fact, this is a normal part of the cleanup process. Of course, this is also something that will be improved in future versions of the add-on, but for now it can be handled quite easily by running Basic Cleanup one more time. This time, we will disable merge distance and enable n-gons. We will immediately set the maximum value to 12. N-gon method, beauty. Then we press Basic Cleanup again. Now we can see that almost all artifacts related to the basic cleanup stage have been removed. The remaining issues are mostly related to the repair holes function. Also, take a look at the vertex count. It has been reduced by more than 4 times. Min edge length is no longer 0. The mesh is now much cleaner and significantly lighter. Next, let's take a look at how the Trim Mesh option works. Part 3. Trim Mesh. The Trim Mesh tool allows you to quickly cut away unnecessary parts of the mesh. In our case, for example, this includes the floor the object is standing on. This makes the mesh even lighter. Once we open the Trim Mesh settings, we enter Trim Mesh Preview mode. The polygons turn blue, the edges become white, and the backside of the mesh is shown in red. Visually, it looks very similar to a blueprint-style display. Here you can choose the trim shape, box or round. In some cases, round can be more convenient for circular objects. Cut mode lets you choose the cutting method. Clean cut creates a clean, knife-like slice, while rouch cut preserves the polygons along the cut boundary. Next, you have the adjustment controls for all three axes, X, Y, and Z, as well as rotation around the Z axis. You can also see the estimated removal value shown as a percentage. The reset button simply returns all settings to their default state. In our case, I will remove the floor by setting the left Z value to 97%. This cuts away the floor and creates large holes at the bottom. We will deal with those holes later in the final part, repair holes. I will choose cut mode, rouch, because it makes the holes easier to work with afterward. If you choose cut mode, clean, I recommend running a basic cleanup once again afterward, because clean cut creates new polygons and can introduce new artifacts after trimming. Also notice the estimated removal value. We gain another 34% reduction here. Finally, we press trim mesh to apply the cut. Now the mesh is even lighter thanks to the removal of unnecessary parts of the object. The vertex count is now about 11.5 thousand. That makes it almost 7 times lighter than the original mesh. Next, we move on to the final, and probably the most interesting part of the QuadLab Mesh Cleaner workflow, repair holes. Part 4, repair holes. This is my favorite feature. At this stage, we can reduce the remaining artifacts in the mesh diagnostics list all the way down to 0. This is where we get rid of tiny holes and large holes. In the repair holes settings, there is a checkbox called Mesh has open borders. Enable it if your object has an open contour that should not be treated as a large hole. In that case, the algorithm ignores the largest boundary loop. A good example would be rocks along a stream. In our case, the mesh is closed, so we leave this option disabled. Next, you can define which holes should be treated as tiny holes by setting Fill Tiny Holes Max Edges. You can also choose the quad method for holes with 4 edges. The maximum value here is 12. In the large hole settings, you can also specify max edges. The default value is 100 and the maximum is 500. Be careful with high values because Blender may become very slow or even freeze. That is why you may sometimes see warning messages in red. Next, you can choose the hole filling method. Standard uses Blender's default hole filling method. It works, but the result is not always very appealing, especially on larger holes. You can also control the triangulation method for quads and n-gons, with beauty set by default for both. Now I want to show how Fill Large Holes works in Smart Mode before applying it to our main mesh. First, I will demonstrate it on simpler meshes: an organic object, a plane, and an icosphere. Here we have something like a mushroom. I intentionally created several holes of different shapes and sizes to see how well the smart algorithm handles them. Let's make a copy of the mushroom. On the first copy, we use the standard method. The result is not very good. The polygons on larger holes become too large, and the algorithm does not preserve the curvature of the mesh. On the second copy, we choose Smart. We enable Follow Surface Curvature, set Relax Strength to 0.80, and click Repair Holes. Now let's compare the two methods. With Smart, the size of the new polygons better matches the surrounding topology, and the algorithm follows the curvature of the mesh much more naturally. Let's also test the plane and the icosphere. I intentionally bent the plane so the effect of the smart algorithm would be easier to see. Once again, we make a copy and compare the two methods. Here, we need to enable Mesh has open borders. We apply the standard hole filling method. On the duplicate, I slightly enlarge the hole so that the number of boundary edges goes above 100. We also see a warning that some large holes have more boundary edges than the current max edges value allows. Hover over the question mark icon to read more. In this case, the message tells us that one hole has 123 boundary edges, so we need to set max edges to 123. After that, the warning disappears. If the hole is even larger, for example, more than 150 boundary edges, you may see another warning explaining that such values can significantly slow down the algorithm or even cause Blender to freeze. Now we click Repair Holes. This is the result we get. We do the same with the icosphere. Now let's return to our main mesh. Before applying the repair, I will manually clean up the hole areas a little so the algorithm can handle them better. Then we apply smart repair holes. Sometimes it is not possible to fix every hole in a single pass. In those cases, it is still useful to locate artifacts with Inspect, clean them up manually, and run smart repair holes again. As a result of the QuadLab Mesh Cleaner workflow, we end up with a mesh that is clean, lightweight, and in very good condition. Finally, if you do not want to miss future QuadLab Mesh Cleaner updates and want early access to new releases, subscribe to our YouTube channel and sign up for the QuadLab newsletter on quadlabtools.com.